90%. For years, Jon Bentley ran the same experiment on rooms full of professional programmers, at Bell Labs, at IBM. He described an algorithm every one of them already knew, gave them 2 hours, and asked them to write it. Around 90% produced code with bugs. The algorithm was binary search. And the story is older than that. The first binary search was published in 1946. The first one that worked for every array size appeared in 1962. 16 years to get 12 lines right. Last lesson closed on a question. The converging pair retired one element per comparison. What if a comparison could retire half of everything that remains? This is that move. The most famous algorithm in computer science, the log-in rung of Lesson 1's ladder, finally cashed in. So here's the plan. Watch it earn the fame first. Then watch exactly how it breaks, including a bug that slept in Java's standard library for 9 years. And then, one template that dodges every trap and hands you every variant for free. Here's the move. On 16 sorted numbers. The target, 53. Probe the middle of the array, 23, too small. And because the array is sorted, that one comparison says something enormous. 53 can't live at that slot, or anywhere left of it. Everything there is smaller still. So discard the middle and the entire left half. One comparison, 8 survivors. Probe the middle of what's left. 41. Still too small. Discard. 4 survivors. Probe again. 47. Too small. 2. Probe. 53. Found. 4 comparisons, 16 numbers. 16 to 8 to 4 to 2 to found. Now scale it. 1,000 elements, 10 probes. 1,000,000, 20. 1,000,000,000 elements, 30 probes. Lesson 1 promised that the halving move buys a growth curve so flat it barely registers as growth. This is the purchase. 30 comparisons against 1,000,000,000 is not an optimization. It's a different universe of cost. And the entire price of admission is one word: sorted. Hold that discard up against last lesson's vocabulary, because it's the same argument at a different scale. The converging pair retired one element per comparison, and the license was sortedness. If the smallest plus the largest is too small, the smallest fails with everyone. Same license here, bigger purchase. The middle element is too small, so everything left of it, smaller still, fails too. One comparison, half the search space proven irrelevant. Not skipped, proven. Last lesson's rule, find the reason you never look back, is at its purest here. Every discarded element carries a one-line proof. But notice what the proof actually needed. Not sortedness itself, just this. The answer to the question, is the value here at least 53, reads across the array as a row of no's followed by a row of yeses. No, 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 yes, yes, yes. One flip, never flips back. Any question with that shape supports the halving, whether or not there's an array underneath. File that away. It's the key to the entire second half of this lesson. So that's the fame. Now the infamy. In 2006, Joshua Bloch, who wrote much of Java's collections library, published a post titled, "Nearly all binary searches and merge sorts are broken." The binary search in Java's standard library, code he had written, had been wrong for 9 years. Here's the line. Mid equals low plus high divided by 2. Looks perfect. Walk the numbers. A Java int is 32 bits. The biggest value it holds is about 2.1 billion. Now, binary search a sorted array of 1.5 billion elements. Eventually, low sits near 1 billion, high near 1.5 billion. Add them, 2.5 billion. Doesn't fit. The sum wraps around to a negative number. Mid goes negative, and the search crashes, reaching for a negative index. Nobody hit it for 9 years because nobody had arrays that big. And the best part? Bloch adapted that code from programming Perls, where it appears next to a proof of correctness. The proof was fine. It assumed mathematical integers. The machine has 32 bits. The fix is one transformation. Mid equals low plus high minus low over 2. Same value, but no sum ever exceeds high, so it can't overflow. The overflow is the famous bug. It's not the common one. The common ones live in 3 innocent decisions every hand-rolled binary search forces on you. Decision 1, the loop condition. While low is less than high, or less than or equal. Decision 2, when the probe says go left, does high become mid or mid minus 1? Decision 3, going right, does low become mid or mid plus 1? 3 decisions, 2 options each, 8 possible loops. A few combinations are correct for some variant. The rest miss the answer by 1 slot, check the same slot twice, or never finish at all. And this is exactly why 90% of Bentley's programmers failed. The right combination depends on which variant you're writing. Exact find, first occurrence, last occurrence, insertion point, each one, written the textbook way, wants a different mix of +1s and -1s. So people memorize one variant and improvise the rest under pressure. Improvising boundary arithmetic is how you lose. But before fixing this, you should watch the worst of the 8 loops actually fail, because it doesn't crash, and it doesn't return a wrong answer. It just never comes back. 2 elements, 3 and 5. The job, the last index holding a value at most 3. Here's a loop you will find in real code bases. While low is less than high, mid is low plus high over 2. If the value at mid is small enough, it might be our answer, and there might be a later one too, so keep it in play. Low equals mid. Otherwise, high equals mid minus 1. Sounds reasonable? Watch it run. Low is 0, high is 1. Mid, 0 plus 1 divided by 2, and integer division rounds down. Mid is 0. The value there is 3. At most 3? Yes. So low equals mid, which is 0, which is what low already was. Loop again. Low 0, high 1, mid 0. Same comparison, same branch, same assignment. Nothing moved and nothing ever will. No crash, no exception, no wrong answer. Just a core pinned at 100% forever. The poison is the pairing. Mid rounds down, toward low, and the branch low equals mid doesn't step past it. The moment the interval shrinks to 2 elements, mid lands on low, and progress stops. Every binary search you write carries a proof obligation almost nobody states out loud. Every pass through the loop must strictly shrink the interval. Now the way out, and it starts with a reframe, not with code. Stop searching for a value, search for a boundary. Take any yes-no question over the indices that reads as no's followed by yeses. For finding 53, the question is the value here at least 53? Early slots? No. Late slots? Yes. Somewhere, 1 flip. The new job description. Return the first index where the answer is yes. That's the reframe, and here's the loop it buys. 2 markers, low and high. Everything left of low, proven no. Everything from high onward, proven yes. Between them, unexplored. Start with low at 0 and high at n, so nothing is claimed yet, and the made-up index n, 1 past the end, stands for no index qualifies, while low is less than high. Probe the middle, low plus high minus low over 2. Ask the question, yes? Then the first yes is at mid or somewhere left of it. High equals mid. No? The flip is strictly to the right. Low equals mid plus 1. When the markers meet, the unexplored zone is gone, and low is standing on the first yes. 4 lines. No special cases. No +1 -1 improvisation ever again. 2 promises to verify, and each proof fits in a breath. First, it terminates. The probe always lands inside the unexplored zone. At low or later, strictly before high, because the division rounds down. So high equals mid pulls high strictly down. Low equals mid +1 pushes low strictly up. Every pass shrinks the zone by at least 1, and a shrinking zone hits empty. The infinite loop from before is structurally impossible, because this template never writes low equals mid. The probe's rounding biases it toward low, and the template always steps past a no. Second, it's correct. Each branch claims only what the comparison proved. A yes at mid makes everything from mid onward a yes, because the question flips once and never back. So moving high onto mid keeps the invariant true. A no at mid makes everything up to mid a no, so low stepping past it stays honest. The invariant holds going in, survives every pass, and when low meets high, it reads, all no before low, all yes from low onward. First yes, low. That is the proof 90% of Bentley's programmers needed and improvised instead. Learn it once, and you never write a different binary search again. Here's the payoff for learning one shape. Every classic variant is the same 4 lines with a different question. Lower bound, the first index whose value is at least x. That's the template verbatim, and it doubles as where would x insert to keep the array sorted. Upper bound, first index whose value is strictly greater than x. 1 character changes in the predicate. Exact find, run lower bound, then look at the slot it returns. Holds x, found. Doesn't, x isn't here, and you already know where it would go. Notice that's backwards from the textbooks. Exact find, the variant everyone learns first, is the derived one. Count how many times x appears. Upper bound minus lower bound. 2 searches, no scanning. Order log in even if x fills half the array. First occurrence, lower bound. Last occurrence, upper bound minus 1. 6 variants, 0 new loops. 1 proof shared by all of them. And these names aren't interview jargon, they're the standard library. C++ ships lower bound and upper bound under exactly those names. Go's sort.search is the template. You hand it a predicate, it hands you the first yes. The written lesson walks the real code. And now the version that shows up in real engineering, where there is no array at all. A shipping problem. 6 packages on a conveyor, weights 3, 2, 2, 4, 1, 4. Ship them all within 3 days, in order, and find the smallest daily capacity that makes the deadline. Where's the array? Implicit. The candidates run from capacity 4, the heaviest single package, up to 16, the whole load in 1 day. And the question, can we make the deadline at this capacity, has the right shape. More capacity never hurts, so the answers read no, 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 yes, yes, yes. That's the only license halving ever needed. Probe capacity 10. Fill days greedily. 322 makes 7. The 4 won't fit. Then 414. 2 days. Yes. So 10 works, and everything above 10 works. Discard it all. Probe 7. 3 days exactly. Yes. Probe 5. Day 1, 3, 2. Day 2, just the 2. The 4 won't join it. Day 3, 4, 1. And the last 4 needs a day 4. No. Probe 6. 3, 2, 2, 4. 1, 4. 3 days. Yes. Markers meet. Answer 6. 4 probes, 13 candidates, and the thing we searched was never stored anywhere. It was a question. You've probably run a binary search this month without writing one. Git bisect. Somewhere in the last 4,000 commits, a bug crept in. The current build is broken. A release from 2 months back is fine. Checking one commit means a checkout, a build, a test run, call it 5 minutes. A linear scan is 2 weeks of machine time. But, does the bug reproduce here, is a no-yes question over history. Commits before the breaking change? No. Commits after it? Yes. It flips exactly once. So bisect checks out the middle commit, builds, tests. Broken? The culprit is in the older half. Clean? The newer half. 4,096 commits, 12 checkouts, an hour instead of 2 weeks, and Git automates the loop. Git bisect run, pointed at a test script, go get coffee, come back to the exact commit that broke production. The same shape runs all over infrastructure. The smallest replica count that survives the load test. The highest request rate before latency falls over. Whenever the job is, find the threshold, and trying one candidate is expensive, you are holding a predicate, and the template applies. One honest beat before the victory lap, because Lesson 2 taught us to price steps, not just count them. Each probe of a big array is a jump. The first lands at the midpoint, the next a quarter of the array away. Megabytes apart, every one a likely cache miss, a full hallway trip. And the prefetcher is blind here. It can't predict a pattern that depends on data. And there's a second toll. The comparison at each probe is a 50-50 coin flip by design. Maximizing information per probe means making the branch impossible to predict, and unpredictable branches stall the pipeline. So at small n, a few dozen elements, a plain linear scan, sequential, prefetched, perfectly predicted, beats binary search outright, and real libraries know it and switch. At 1 million elements, none of this matters. 30 scattered probes cost microseconds. Scanning 4 gigabytes costs hundreds of milliseconds. The latter from Lesson 1 is undefeated. But on disk, 30 dependent reads is a catastrophe. So databases fatten each node to thousands of keys and discard 99.9% per read instead of half. That structure is the B tree, and part 2 of this course builds it. And that closes the module, linear structures and their patterns. You can now build the dynamic array, the string, the list, the stack, and the queue from raw memory up, price every operation they offer, and swing the 2 patterns that make flat data fast. Pointers that never look back, and a boundary you can have your way to. That toolkit is most of what production code does all day. Now look once more at what binary search actually does, because there's an idea hiding inside it. It takes a problem and shrinks it to a smaller copy of itself. We wrote it as a loop, and for binary search, a loop is the right call. But that instinct, solve the smaller version of the same problem and trust the answer, is one of the deepest ideas in computer science, and it has a name: recursion. New module. We start with the machinery underneath. Every function call you have ever made pushes a frame onto a stack, and once you can see that stack, recursion stops being magic and starts being bookkeeping. The call stack, made concrete. See you there.